Hi there! Welcome to week 4 of Embedded Serial Buses. This is it, the final week where we're going to bring it all together. I am Alexander Rowsell once again for the last time. There's my email on screen. Once again, if you have any questions, you can email me, but you're also encouraged to post the questions to the comments page of the class page on HackadayU so that other people can see the questions and therefore the answers to them. So, I just want to go over some errata quickly, some mistakes that were made in the past few weeks. I2C peripherals do have FETs that connect to SCL. In the first week, I showed in the schematic that they don't. Not all of them do, but this is how they do clock stretching for I2C devices that implement clock stretching. This is a feature that some peripherals use to tell the controller to wait. They're not ready to send data yet, they're processing or whatever. This is an alternate option to how we implemented it by polling the device to see if it's ready. You can also have it hold the clock line low until it's ready. Of course, that prevents you from doing any other communication, typically I find that the polling method does work better, but yes, some I2C peripherals do have FETs connected to SCL. Another mistake I made, unfortunately, the SHT31 is different from the SHT21. The board that we linked for you to buy to do some of the demos in this course from Adafruit, unfortunately has a different command set. That was already resolved. The Git branch in week 2 was specifically set up so that people with the SHT31 could still use the code. This was my mistake. The data sheet I have was for the 11 and the 21, and I assumed that the 31 was in the same family and therefore would have basically the same register layout, but it turns out it's completely different. But the code is there for you to look at if you need it. Another question that came up during a question period was about one-wire and software delays, and the only reason I did it experimentally is because I typically will calculate roughly what 1 microsecond of delay should be, and then I'll multiply that out as needed for one-wire delays. But then, of course, you're going to have to tweak that a little bit because it takes the chip time to switch GPIOs from high to low. There's other things that can slow it down a little bit, so that's why you can do it mathematically, but I tend to sort of start with some mathematical calculation of what 1 microsecond would be, multiply it, and then tweak it as needed to get exactly the right lengths. Basically, you want to see it decoding properly in the logic analyzer software. Once it's decoding there, you know that it'll be according to the standard, and it should work with any one-wire device. There were a few small issues here and there in the code. The GitLab repository always has the latest working code, so make sure to check that out. It's at gitlab.com/frozenelectronics/HackadayU serialbuses.git, I believe, but don't quote me on that. It's on the class page on hackaday.io. It's on the left-hand column. You'll see a link to the GitLab source code repository. That should take you right to it. Any other errors that come up, because I'm not perfect, far from it, they'll be corrected on the course page. These videos might also be updated in the future with improved information or corrected errors. So check back to see if there's improved versions of these videos, or keep an eye on the course page. If any errors come up, that's where they will be put. So this is our final week together. This week we're going to sort of wrap things up with a small project that combines everything we've learned so far. We're going to be taking data from both one-wire and I2C and then displaying it on an I2C enabled LCD screen. These are very cheap and ubiquitous and easy to get on eBay if you want to actually run this code. At the end of this, we're going to do an optional simple test that shows, it's just a way for you to self-evaluate how well you absorb the material. Of course, there's not going to be any grades or homework or anything. If you have trouble answering the questions, then go back and refer to things that you need to. But it's again, the most important skill is being able to find information quickly and not necessarily having everything memorized. So it's a fallacy to think that if you don't do well on this test that you didn't learn anything. Once the ideas are in your head and you find the information, the second time around you'll be able to absorb it much more quickly because you've already done it once. So we're also going to touch on using logic analyzers, an extremely important tool if you're working with embedded serial buses. Having a logic analyzer is priceless. It makes the job so much easier. So first, let's talk about adding the LCD. So standard character LCDs come in a variety of sizes, 16 by 2, 20 by 2, 20 by 4, and they use a parallel interface for writing to the screen. Now, for a lot of reasons, you might not want to use a parallel interface, and pin count is usually one of those reasons. So we can get these I2C backpacks. Adafruit sells them, and of course you can also buy cheaper versions. These things have been around for a long time on the usual suspects, eBay and Amazon and such. They essentially add an I2C GPIO expander. They convert the LCD interface into an I2C interface. There's also SPI versions available that essentially use a shift register chip. This moves a lot of the complexity from the hardware into the software, but it reduces the pin count quite a bit. You need typically a minimum of 7 pins to connect to the parallel interface, and this will reduce it down to 2 for I2C. So that complexity in the software is often a worthy trade-off for something reducing the pin count by that much. We're going to be essentially bit banging the LCD via I2C GPIO, so hopefully that's as clear as mud. So here's a picture of one of these backpacks and attached to an LCD. So it basically solders directly to the pins along the top there. We've got the main I2C chip on there is the PCF8574. This is a fairly old chip, which you can tell based on the prefix PCF. That was the prefix used when Philips was still the one maintaining the I2C standard before it was bought out by NXP. And it's a very, very simple chip. We'll get into the details about it. It has a contrast potentiometer, which is a really nice touch. That's something that you need to provide anyway if you're driving an LCD. There's a few pins on there that you need to connect a resistor between, and depending on the value of the resistor, it changes the contrast of the LCD. So by having that potentiometer on the back, you can quickly just adjust it to get the correct contrast, and then it's set, which is really nice. It's got the I2C connections on the side there. All it needs is power, ground, and then the 2 I2C lines, SDA and SCL. We've got some I2C address selectors, which is really nice. So we can change the address of the PCF8574 in case you want to have multiples of this chip on the same bus. You can add resistors there, and by changing the values of which of those pins you pulled to ground, it'll change the address of the PCF8574. So that's a super, super handy feature. There's also a constant current backlight driver. Those 2 pins there on the left, you can either short them together to use the onboard driver, or you can drive one of them directly and that connects to the backlight. But if you just connect those 2 pins together, they'll come with a jumper on them. Then it'll drive the backlight with a standard current, and it'll be, you know, nice and bright and readable. So that's what the backpacks will look like. The PCF8574 is, as I said, a GPIO expander. You basically control an 8-bit GPIO port via I2C. It's a very basic device. When you write to it, whatever byte you write gets written directly to that 8-bit port. And if you read from the device, it changes all the pins to inputs and reads whatever's on them. So you don't have a lot of control, but it's very reliable and works really well. The Adafruit backpacks and some of the more expensive ones will use the microchip 2300X series. They have much more advanced control, analogous to what you would see inside a microcontroller's GPIO section. So you can explicitly change the pins between inputs and outputs. You can have an interrupt whenever a pin changes state. You can set pins up as open drain or have slew rate controls, which is really nice. And they can also have pull-ups on the pins, which is nice. The cheap imitation boards work absolutely fine, but they're much more likely to contain a PCF8574. The code that I've written, of course, is for a board that uses the 8574. And so that's what I'm expecting with this code. Because of the way it works, the direct write to the output port, we have to do some weird things in order to send commands and text to the LCD. These LCDs have a sort of standard interface, and the way it works is you send a command or a character to it, and then you have to latch it in by setting a pin high and then low, the enable pin. It needs to be driven high and then low again. And we're running in 4-bit mode, so each command has to be split in half into 2 nibbles, 4 bits at a time, and sent separately. So the LCD library I wrote and added to the GitLab repo does this all for us, and it's quite easy to use. If you're curious about how it's actually connected to the LCD, the top 4 bits are connected directly to the data pins on the LCD, and then the bottom 4 bits are connected to the LED controller. You can actually turn the LED backlight on and off in software, which is cool. The enable pin, the read-write pin, and then the RS pin, which basically tells it if what we're sending is a command or if it's data. So basically our software has to work with that connection set and then make sure that the data that gets sent to the LCD makes sense. We're also going to be using, just because I happen to have it on the Sensor Hub booster pack, and these are also very common and cheap to get, BMP180 pressure sensors. The booster pack I have been using for all these examples also has this sensor on it, so I decided to display this info as well. If you don't have a BMP180, you can just remove the BMP180 files and remove the include statement from the main.cpp file, and then there's a few BMP commands that are really obvious. You just have to delete those as well. But the function that the BMP180 class implements is just called get pressure. It returns both the pressure and the temperature, but we're only going to be displaying the pressure from this chip. Now, if you're curious, I encourage you to check out the BMP180.cpp file. The algorithm that's used to convert the raw data that comes back from the BMP180 into both temperature and pressure, it's this crazy algorithm. There's so many lines of formulas you have to do. You know, you're multiplying all these values together, dividing them by, 2 to the 10 or 2 to the 12, and bit shifting, and it's just this huge series of steps. Luckily, the way it's written in the data sheet is very easy to read. You can basically copy and paste it into C, more or less. And I've basically done that. And it comes out the other end with a pressure value that makes sense, which is good. I don't actually know what the algorithm is doing. I have absolutely no clue how all those formulas work. You'd have to really understand how this particular chip works to understand what it's doing, but it's all handled for us in the BMP180 library. We're going to be displaying temperature and humidity from the SHT chip, either the 21 or the 31, and we'll be displaying pressure from the BMP180. So, writing to the LCD. Now, the LCD class has 2 20-character arrays, one for each line of a 20 by 2 display. These displays don't necessarily have just 2 lines. There are versions that have 4 lines, and of course some of them have 16 characters or 20 characters wide. When you create the LCD instance in the main file, you'll see that the second argument to the constructor function is the width of your display. So you need to either put 16 or 20 in there. This just prevents it from writing past the end of the line. It doesn't really actually matter all that much if you write past the end of the line. Technically, it'll eventually wrap around to the second line, but this is just to make the code sort of nice and neat. Simply put whatever text you want displayed into those 2 arrays and then call the update function on the LCD object. and it'll take whatever's in those two arrays and print them to the screen directly. We're going to be using sprintf again. If you saw the code over the past few weeks, you'll notice I've been using sprintf to send data to the console via the UART. I was using this for debugging and just for a basic output display, and we were using sprintf. It works the exact same way as printf does. The only difference is instead of writing to a standard output like you would on a computer, you're instead writing it into an array or into a pointer to some memory. So we're going to be using sprintf to format these values into these two lines, putting them into those two arrays for line 1 and line 2, and then we call the update function and it'll display that. If you're interested in how the LCD actually works, all the commands are inside the header file. And if you want to learn more about how these types of LCD displays work in general, which is sort of outside the scope of this course, do a search online for HD44780. There's a whole bunch of data sheets around. The HD44780 is a chip that was made by Hitachi many years ago and has become ubiquitous. It's used to drive all of these different character LCDs from 16 characters wide to 20 characters by 4 lines. I think you can even get 40 character wide versions. They all use the same chip. So knowing how it works is something that's just good to know. If you take a look at how the library works, you'll get sort of a hint about how it works, but looking at the actual data sheet is always better. One of the cool things about it is that it's possible to create custom characters. For example, we could add the degrees symbol for the temperature display if we wanted to. I leave that as an exercise to you if you want to give that a try. If you look at the LCD library, you'll see that there's a way to send characters and a way to send commands. You would need to send a command and then send the data that represents that symbol. But I'll leave that as an exercise to you. So here's a screenshot of it working. This is the display connected to the MSP430. As you can see, it's displaying humidity 49.66%. The temperature was 23.22 when I took the picture, and the pressure was 98.944 kilopascals. Now, I know that kilopascals is a very Canadian thing. I don't think any other countries use kilopascals. I know the US uses inches of mercury, I think, and I know that other places use millimeters of mercury. There is a formula to convert between them quite easily. So if you want to change that to display inches of mercury, that would be very easy to do. And this, the display I has is the blue display, which I really like that blue with the black writing. It's very easy to read. So basically, we're using I2C and OneWire to collect data, well, I2C mostly, and then the OneWire device is verifying that we are the correct board. So that silicon serial number, as they call it, the 2401 OneWire chip, it's the code that was in there from last week. It reads from that chip, makes sure that the serial number matches what it should be, and then it will let the code run if it's correct. If it's not correct, it won't let it run. If you don't have one of those for that demo, you can just delete that section or comment it out and it'll go past it. This actually bit me when I was prototyping this. I was trying to figure out, why isn't this working? Everything should be fine and everything's wired up correctly, or so I thought. And then it turns out I had actually wired this chip incorrectly, and so the code was doing exactly what it was supposed to be doing. The comparison was wrong, and so it wasn't running the code. This is sort of a basic but complete example of a real-world usage of serial buses. You have multiple inputs that are different sensors. You have an output, in this case that's a display, to actually display this data to the user. And this is the sort of thing that you would actually see on a real product in the embedded world. We could easily swap out that I2C temperature sensor for a OneWire sensor if we needed an immersible version, for example. The DS18B20 is a very common OneWire chip you can get in these little encapsulated tubes that are all sealed up, so you can insert them into liquids to get the temperature of liquids, or you can push them into soil. Basically, anywhere you wouldn't want to put electronics, it's nice and sealed so you can measure the temperature. It would be very easy to swap out the I2C temperature sensor to get the data from a one-wire device instead. The project is written all in C++, just like all the other weeks, which makes reusing the libraries in other projects quite simple. All the code that I wrote for this course is licensed under the Mozilla public license, so it's all fully open source. You can do whatever you want with it. You can modify it. You can use it in your own projects. Feel free to hack at it as much as you like. It's there for you to use. I did basically a 1.0 release of the completed code. I took the Code Composer Studio project folder and zipped the whole thing up. This was something that came up in the question and answer period last week, or maybe it was on week 2. Someone was asking if I could provide the full project so that you could import it directly into CCS. That is up on the GitLab repository site. If you look under releases, you should see one there, and you can download the zip file. And once you extract it, you should be able to import that folder directly into your Code Composer Studio workspace, and it should just work as long as you're using Code Composer Studio 10, which is the latest version. So yeah, that's there if you want it. And of course, the Git repo you can just clone as well and mess around with the code that way. Look at the different branches and so on. All right, so let's just take a very quick look at this LCD library I wrote so we can see how it ties into I2C. It has the LCD address and all this information in the header file, all the different instructions that the LCD needs. The class has that constructor function. Just like the other sensors we have, we basically need to give it a connection to the I2C bus. And then in this case, we tell it how wide our display is, either 16 or 20 characters. And the only other command that you'll need to access is that update command, which whatever is in these two arrays, line 1 and line 2, that will then be displayed. If we actually look at the code for how this works, you'll see that it's fairly simple. We basically load whatever command we want to send into this LCD out variable, and then we call the send function, which is down here. And whether or not it's a command or not, it does something different. Now, this is that finagling I was talking about. Because of the way the PCF is connected to the LCD, we have to do all this weird bit shifting and stuff where we take each half of the command. So this first 3 instructions, we're taking the top nibble, and then we are basically toggling a pin on and off. That's why it goes from 8 to C to 8. We're just turning the 4th bit, which is that enable pin, on and then off again. Then we send the lower half of the nibble, which is, and then we do the same thing. We turn that enable pin on and off. This is loading all these commands into a buffer, basically, and then we send that out over the I2C bus, and it'll send all these out in order, which will, in turn, manipulate the GPIO on the I2C expander chip, because whatever we write to it is literally what comes out on the pins. I mean, there's not much in the data sheet for this chip. That's basically all it is. So if it's a command, we have a certain bit off. If it's not a command, then we turn on another bit, and then it goes 9D9 because we have another bit on. So this section is just doing all that juggling for us. The update command, as you can see, it just takes line 1, loops through it, and sends it out, character by character, out to the LCD. And then it does the same thing with line 2 after it repositions the cursor. So it's a very simple library. I mean, you can see there's not much here. This is what is nice about these GPIO expanders, is that, yes, this is sort of complex, this function, but if you have an I2C library, it doesn't really need to do a lot. You just need to have all the commands that you need for the LCD, and then just send them out in the right order, and that's basically it. So the way we've put this into our main function, we've got the one wire thing at the top. So if you don't have a one wire, if you don't have one of those 2401 silicon serial numbers, you can just delete this whole section here, and that's fine. If you don't have the BMP180 for pressure, you can delete this line, and as well as updating line 2, and then you'll just get the top line with the humidity and the temperature. But basically we get the humidity and the temperature, then using string formats, which is something you'll learn about in C. It's basically a way to turn variables into strings using this special syntax. It gets displayed, it gets stored, pardon me, in line 1. Then we get the pressure, which actually gets the pressure and the temperature again. And then we take the pressure and we stick it in line 2. Pretty simple. And then we call display.update. I still have the console.debug info in here, so that if you don't have an LCD, you can still see exactly what it's sending, and you can still play around with these lines to get it working for you. And then just like before, there's a timer interrupt, so it goes to sleep, and then every 6 seconds or so it'll wake up and update the display. If you want it to take longer than that, you can change this number here to 927C, and then that'll be about 60 seconds. So that's basically the only major differences from last week's code, is the addition of this LCD code and the BMP code. So yeah, here's what I was talking about. So we need to read all these values from the chip, and then to actually convert the data from the chip into a pressure, we have to go through this crazy series of formulas to first calculate the temperature. Once we have the temperature calculated, then we use that to calculate the pressure. But just look at all these variables and all the stuff it does, all the processing and division and adding and multiplication, and it's just crazy. And then finally at the end we get pressure, and we actually get pressure in pascals. I then divide it by 1,000 because I'm Canadian and we use kilopascals for some reason. At this point, if you wanted to change it to inches of mercury, you would just take this pressure value and then do a conversion to it to go from pascals to inches of mercury. And that would be basically the only change you would need to make. And then the header file for that BMP180 is quite simple. There's just the 2 commands, sample pressure and sample temperature. And then basically, once again, we need to give it a connection to the I2C bus. We've got the 1 command to get pressure. It returns it in these 2 pointers. And that's it. So very, very simple, actually. It works great, and it's a great demonstration, especially if you have a logic analyzer and you can actually probe what's going on. This is an excellent way to see what's actually going on the bus when a fairly complex series of transactions is going on. All right, so let's talk about logic analyzers briefly. So logic analyzers are super, super useful tools. If you can't afford one, you can still do work without them, but they're super, super useful to have. They're a class of tools that sample a digital signal and display it to the user. You've seen traces throughout this course. You've seen snapshots from a software I use called PulseView, which I use to interface with my logic analyzers. Essentially, a logic analyzer is basically an oscilloscope with hysteresis. So if the voltage goes above a certain level, it shows up as a high to the logic analyzer. If it goes below a certain level, it shows as a 0. You can configure typically what the logic level is that you're working with, depending on if you're working with 5 volt logic, 3.3 volt logic, etc. Because it's a digital signal that it's sampling, it can forego all the complex analog filtering and stuff that's needed in an oscilloscope. Therefore, you can get them quite small. You can get them into these small, tiny little USB logic analyzers. Most logic analyzers, the software will include a serial bus decoding function, which is just, I can't even put into words how useful and important that is. You've seen snapshots of it through this course. A good logic analyzer decoder will show you exactly what each byte value is, or what those bytes actually mean. For I2C, it'll show you start conditions and stop conditions. For UART, it'll show you break conditions. It just tells you everything you could possibly need to know about what's going on the bus. Even logic analyzers, older ones that don't have serial decode, can still be useful, because then at least you can see what's going on the bus. You can decode by hand if you have to. Even just being able to see things like, is the I2C bus working? Am I seeing a stop condition and a start condition? Does the data look like it's at the right speed? That sort of thing can be super, super helpful. So when I was creating the code for this course, I used both my ChronoView, which was a somewhat pricier logic analyzer that's unfortunately no longer available. The company went out of business a few years ago, as well as a cheap 8-channel, they call them FX2 LAFW. I guess that's the name of the chip inside that it uses. A cheap 8-channel logic analyzer that I got off of eBay or Amazon a while ago. So just another thing I wanted to point out is that with PulseView and with most logic analyzers, you can pick the sampling rate, because of course it's sampling a digital signal at a certain speed. So just like an oscilloscope, you have to make sure that the sampling speed, remember Nyquist's theorem if you've ever looked at that before, the sampling rate has to be at least double the speed of whatever you're looking at. So if we're looking at, say, a 1 megahertz I2C bus, we need to sample at least 2 megahertz, preferably much higher than that, 4 or 8 megahertz, to get good detail of what's going on the bus. 2 megahertz, you can recreate what's there, but the higher the sample rate, the better. The nice thing about these logic analyzers that work with PulseView or any laptop or PC software is, unlike a benchtop logic analyzer, it can take advantage of the fact that your laptop has a huge amount of memory. I mean, my laptop has 16 gigs of memory. That's a lot of samples. So you can have a fairly high sample rate, and you can also sample for a very long period of time, which can be super useful if you're trying to pick out a glitch that happens on a serial bus, or something that doesn't happen very often. Super, super useful in combination with a laptop. Now, these low-cost USB analyzers are basically all based on the Salier. If your budget allows it, it's always worth buying a higher quality one like the Salier Logic Pro. They're a great company. Their software is excellent, and that's one of the things that you get if you buy the real thing, is you get access to their software. You get support from them and from their community, and you're helping support a really cool company. These low-cost clones of the Salier basically work with PulseView, which is a fully open source and free software that you can use on Windows, Linux, and Macintosh. But this is a tool, and if you're going to get into embedded serial buses or embedded design at all, it's worth buying a decent quality one. That's why I got my ChronoView. It has a sampling rate of up to 100 megahertz, which is really good for when you're sampling higher speed buses. These cheapo ones typically will only go to about 8 to 20 megahertz if you're lucky, but they're under 20 bucks. So you basically can't beat the price. And they're great if you're on a strict budget, or if you're just doing this as a hobby. 8 to 20 megahertz is fine for I2C and UART and one-wire, and even low-speed SPI. Up to 5 to 10 megahertz generally you can get away with, which is perfectly adequate for a lot of the stuff that you might be doing as a hobbyist. As I said, PulseView is an excellent free and open source piece of software that works with a wide variety of USB and benchtop logic analyzers and oscilloscopes. You can actually connect Rowsell oscilloscopes, Handtech oscilloscopes, and a few other ones as well. I think you can even connect the Keysight ones and some of the Tektronix scopes as well, which is a great way to get live data on your laptop so that you can decode it using PulseView. Often on oscilloscopes, the serial bus decoding is an optional extra, which can cost quite a lot of money depending on the manufacturer. This is a great way to get serial decode just by adding a USB cable, essentially. PulseView can decode. The list is huge of all the different serial buses and parallel buses it can decode. You know, you've got all the major ones, UART, SPI, I2C, one wire, but then you've got CAN and LIN, FlexRay, like the military standard ones, the ones that are used on airplanes, just tons and tons and tons of stuff. For analyzers, as I said, for analyzers which support it, it'll use your computer's RAM as the sample storage, so you can get, you know, a huge amount of data collected, which is really nice. So if you happen to already own an MSO, which is a mixed signal analog oscilloscope, take advantage of the logic inputs. You can, just like with any oscilloscope, you can probe a logic circuit with the analog input, and that can be very useful if you're trying to troubleshoot something weird happening on the bus that you can't see on the logic analyzer. There might be spikes or interference or noise or something, but if you have the logic inputs, take advantage of them, because that'll free up your analog probes for something else. And benchtop MSOs will typically give you a much higher sample rate than what USB analyzers can do, and therefore it'll give you much better resolution. You'll be able to see smaller spikes that may happen, any weird transients that happen. And if they do have decode, it'll be real time. PulseView has to read the data in sequentially and then decode it. So if you want real-time, high-speed decoding, often the only way to go is with an MSO. If you only own a 2-channel digital scope, as I said, you might still be able to connect it to PulseView or any other software that does decoding via USB. Or you might be able to add serial decode as a software upgrade. Sometimes that's really expensive. Sometimes there's ways to get it for free, so look into that if it's an option. But even just being able to probe your signals without decode, even if you just have an old analog scope, it can be super useful. Just seeing that the bus is there and working can help you figure out what's going on sometimes. So on my old HP54645D, it has a 16-channel logic analyzer, but it doesn't do any decoding at all. But I used to use it to decode I2C and SPI by hand. So definitely tedious, definitely not the most fun thing to do, but is definitely doable and helped me solve a lot of problems. So even older equipment is still perfectly valid. So if we take a look at some of the features of PulseView, one of the really nice ones is being able to save your captures in a compressed format. All of the example traces that were used in this course are available to download on the course page. You can then open them in PulseView, zoom in, take a look around. Even if you don't have a logic analyzer, then you can take a look at what the bus actually looks like. You can play around with the decode settings. They are the files ending in .sr. That's a good way to get a good up-close look at how the decoding works and what the bus actually looks like. Okay, quiz time. So get a piece of paper if you don't already have one handy. Open up a blank notepad or other Word document if you want to write down your answers. And here we go. So, questions and answers, by the way. The question slides are going to come first, so you can write down all your answers. Each slide will have one or more questions on it. And you can pause if you want to think about it for a minute to write down your answer. Then at the end, we're going to go over the answers. They're going to be listed in separate slides at the end. So don't worry if you get things wrong. This is just basically a way to check and see how much you absorbed the first time through the course. Often it takes time as well as practical usage to become proficient in a subject. And as I said, the most important thing is being able to locate information, knowing where to look for information. So with all these examples and with I2C and one wire, just like we looked at in week 2 and 3 when we were actually implementing I2C and one wire libraries, is just knowing where to look for that data. So even if you don't know the answer to these questions, you will now at least know where to look. And the second time around, if a few months from now you need to look up some of this information, the fact that you've already gone over it once means you'll be able to pick it up again really, really quickly. So here we go with question number 1. This is a fairly easy one. If you remember, which I2C signal goes low first during a start condition? So think back to what a start condition is. Which of those two signals on the I2C bus goes low first? Which one goes high first in a stop condition? So if you think about the stop condition, which of the two signals goes high first? And why is this? Why do they go in the order that they go in? So I'll give you a minute to write down your answer or think about it. You can pause if you need to. Question 2. How many bits does an I2C address have? So think about the chips we've worked with and how long those addresses are. How many bits does a one-wire address have? You can also answer in bytes for the one-wire address. Take a minute to write those down if you need. Question 3. At the end of every byte transmitted on an I2C bus, there is an additional bit. What is this bit called? Which side sends it? Take a minute to think about that. Write down your answers if you need. You can pause. What happens if it isn't sent? Question 4. What are the most common speeds that I2C runs at? So there's a few standard speeds that you'll often see I2C running at. What are the most common ones? Can you remember the standard names for each speed? Often they'll be referred to by these names, and you'll have to sort of remember what speed that they're referring to. What speed does one wire run at by default? So remember, one wire runs at a very particular speed. And how fast does it run in overdrive mode? Remember that there's a fairly simple relationship between the speed it runs at by default and how fast it runs in overdrive. So take a minute to write those down and think about it if you need. Question 5. What are the names of the 4 addressing commands in OneWire? Remember, each of the names ends in ROM. So there's 4 of them that are used to address OneWire devices. And each one will be blank ROM. Which of these do we try and avoid? There's one of them that we try and avoid using if we can. Why do we want to try and avoid using it? That's sort of a bit of a longer answer, so take a minute, pause if you need to write it down. Question 6. What is the name of the mode in which a one-wire device is powered from the data line? There's a particular mode that one-wire devices can run in where they're powered from the data line. What is that mode called? How does it store power internally from the data line? Question 7. What happens if 2 I2C devices start talking at once? If they both start talking at the same time, what happens? And what is that called? How does this resolve itself? If 2 devices start talking at once, what happens? How does that fix itself? Question 8. How can a one-wire controller, so a microcontroller typically, tell if more than one device responded to a read-ROM command? That's the command where it reads the addresses from any device on the bus. There's a specific way it can tell if more than one device responded at the same time. There's something it should do if this occurs. There's a specific series of steps it needs to take to resolve this situation. What should the one-wire controller do if it detects that more than one device responded? All right. Finally, question 9. What is the major similarity between one wire and I2C? There's one big thing that they share, which makes them quite similar to each other. Why does the amount of capacitance on either bus matter? Why is that an important thing to know? And how does it affect the bus? Why does this matter at all? Okay, so go back if you need to, if you missed any of the questions. Oh. Okay, go back if you need to. Take a look at the questions again if you missed any of them. We're going to go over the answers now. So for question 1, which line goes first for a start condition? It's SDA. And the same was the answer for question 2 of question 1, part 2 question 1. SDA goes high first in a stop condition. In order to signal a start or a stop, the data line must change while SCL is high. This is the only time this is allowed. So that is why SDA has to change first. It's the only way to signal a start or a stop. Question 2, how many bits does an I2C address have? It has 7 bits, and once the read-write bit is added, they're 8 bits. So either of those answers is technically correct. One-wire addresses have 64 bits or 8 bytes. Either of those is an acceptable answer. Question 3, that extra bit at the end of I2C transmissions is called the ACK or NAC bit. The side that sends it is the one that is currently listening. So whatever side is currently receiving data is the one that sends the acknowledges or not acknowledge. And if it's not sent, if we don't send an acknowledge, it becomes a NAC because of the pull-up resistor. So by default, it goes into a known state and transmission ends. Okay. Page 2. Question 4. The two most common speeds for I2C are 100 kilohertz and 400 kilohertz, which are called standard mode and fast mode respectively. 1 megahertz is called fast mode plus, and 3.4 megahertz is high speed mode. So those are the common names as well. One wire runs at 16.7 kilobits by default, or 16.7 kilohertz is an acceptable answer, and it runs at 167 kilobits per second in overdrive mode. That's exactly 10 times faster. Question 5. The main one-wire addressing commands are called match-ROM, read-ROM, skip-ROM, and search-ROM. And it's the last one of those, search-ROM, that we try and avoid because the algorithm is fairly complex and difficult to implement. If you need it, of course, then it's, you need it. But if you don't need it, then you may as well just try and use read-ROM or skip-ROM if you can. Question 6. The mode that one-wire devices use when they're powered from the data line is called parasitic power mode. It's kind of like a parasite sucking on the data line, I guess. It stores the charge internally through a diode into a capacitor that's typically about 80 picofarads. Okay, answer is page 3. So if two I2C devices start talking at the same time, bus arbitration occurs. That's what it's called. It's non-destructive with I2C. Each device checks to make sure the state of the bus is as they set it. So if there's a mismatch, then another device is transmitting and they must wait for a stop condition before trying to transmit again. Because of the pull-up resistor, bus arbitration is automatic and it resolves itself without damaging any data. So we don't need to implement it in software. It's taken care of for us just by us checking to make sure that the bus is as it's supposed to be. Question 8. One-wire devices can tell that more than one device responded because the CRC checksum at the end of the data, at the end of the address, will be incorrect. If that happens, it should then use the search ROM algorithm to enumerate every device on the bus and get all their addresses individually. And question 9. The major similarities are that both use external pull-up resistors and open drain outputs to control the bus. And because of this, too much capacitance will slow bus communication down. This can be corrected with a stronger pull-up resistor by lowering the value of the resistor, or by somehow decreasing capacitance on the bus by removing devices or by shortening the cables. So, how did you score? Did you get most of all 9 questions correct? If you got most or all of them correct, awesome, good work. That's really awesome. If you missed questions, that's totally fine. As I said at the beginning, it's more important than memorizing things is knowing where to look to get the answers. So review the slides if you need to. You can download the slides from the class page, or you can review the videos for the earlier weeks, or there's lots of other resources on OneWire and I2C out there. If you find any good websites that you really like, make sure you bookmark them, because when you run into issues, it's good to have bookmarks handy of websites and locations you found that give you the information you need quickly. And again, if you want a textbook for I2C, Mastering the I2C Bus by Vincent Hempy is basically the best and only textbook out there. It's available from Elector, which is a European electronics outlet. So you have to pay in euros and have it shipped over here. Sometimes they pop up on Amazon. It goes into a huge amount of detail on I2C. And includes a whole bunch of example circuits. If you buy it directly from Elector, I think it comes with PCBs in the book that you can then solder up, and you have some example circuits to play with, which is really, really cool. So congratulations, you've made it all the way to the end of Embedded Serial Buses Part 1. Make sure you try implementing all these examples on the real hardware. Make sure you go back, if you've got your MSP430 and your SHT31, make sure you run those examples. Pick up a logic analyzer if you need, or the other things we use, the LCD with the I2C backpack, the BMP180, any one-wire devices that you want to play with. Give it a try. The best way to learn is by following the examples, seeing how they work, and then adapting them to use with other chips. If you run into issues, you can always comment on the course page. There's now a course chat room on hackaday.io, which is really cool. You can always email me, or you can ask any online community that's involved in electronics. There's quite a few of them, Hackaday, of course, but there's many others out there. Stay tuned to Hackaday Twitter and the Hackaday email newsletter for information about part 2 of this course, which isn't confirmed yet. If we do the part 2, it'll be covering UART and SPI. It'll probably take place in January. That's it. I really want to thank you for attending this course. If you have any feedback on the course, that would be really, really appreciated. Some of these videos might be re-recorded for any small errors that I made. If there's things you liked or didn't like, let me know. That means a lot to me. I hope I did a good job. And a huge thanks to HackadayU for doing this, for partnering with me to teach you this course. They're working on nonprofit education. It's a really, really cool model. Pay what you like. And I really, really hope you learned something. And now you are all officially, you can put this on your resumes, you are official embedded serial bus ninjas. You are an I2C ninja and an one-wire ninjas. So you can get out there and chop up any circuits and use your ninja skills to fix any I2C or one-wire problems you come across. So thank you so very much, and hopefully we will see you for part 2 of the course.